Hello, everybody. Welcome back to our another day of the Algebraic Graph Theory seminar. Today, Giusy Monzillo is going to tell us about a Q-polynomial property of bipartite graphs with a uniform structure.
Okay. Hi, everybody. Thank you very much for being here. Thank you for inviting me to give a talk in this seminar series. So, as you can see from my first slide, for the first slide of my talk, I'm going to talk about, to introduce you to the project, a joint work with some of my colleagues here in Koper, Slovenia. So plus Štefko Mitra also actually, well, she's not here anymore, but we still work together. We started 3 years ago on this project. And that's the title, that's the content actually. So is the Q-polynomial property, actually it's not the standard usual way that maybe some of you have in mind. So it's like extended generalized version of bipartite graph that have so-called uniform structure. So you see in this title we have already a lot of concepts that are involved, and of course, they need to be explained and give in the next few slides. But first, let me spend a few words on this Q-polynomial property. So for decades, maybe even more, this property has been studied and has been associated with distant regular graph. Since there's introduced this for a deeper study of this irregular graph. And recently in 2023, Terwilliger uses some properties, additional property consequences of this property on this irregular graph to extend this notion to a graph that are not necessarily distance regular. So within this concept, it could be interesting to provide constructed examples, so graphs that are not distant regular, but enjoy this property, Q-polynomial, we say with respect to a vertex. And of course, we will focus, as you can see again from the title, the study, we focused actually the study on graph that are bipartite with a uniform structure. Okay. So, as usual, we need to fix some notations and record some preliminary results. So, through the slides of my talk, gamma will be also always representing a simple connected undirected graph with vertex-set X and edge-set R, that X and Y two vertices will be the distance between two vertices. Epsilon of X will be the so-called eccentricity of X, capital D, the diameter of gamma. And then once we fix a vertex, we will consider the so-called subconstituent gamma I of X, of gamma with respect to X, that is made of these vertices. So all the vertices Y that are at distance I from X. So actually it's like when you have such a graph, we can fix a vertex X and partition all the vertices with respect to the distance with the prescribed given one, that we get these layers that we call subconstituents. And as always, and usual, we need to also consider some vector space and algebra of matrices, particularly V will be the vector space over the real numbers, consisting of column vectors indexed by the vertices of the graph, and M will denote the algebra of matrices over the real numbers, whose rows and columns are indexed again on the vertices of the graph. Okay, once we have, let's say, this framework, we can then now recall two important matrices for our aim. First of all, a very well-known one, that is the adjacency matrix that we say A, we call A, for the graph gamma. So it's a 0-1 matrix, and we have precisely in the XY entry 1 or 0, if respectively the two vertices, X and Y, are adjacent or not. Okay, and now we recall something that maybe it's not so familiar to everybody, most of you is not known, because something that, let's say, we define in this new project. So we need to fix now here a vertex X and consider the corresponding eccentricity, epsilon. Consider also pick some pairwise distinct scalars from the real fields that we denote by theta I star, and we have epsilon plus one of them. And then we can define a diagonal matrix that we call A star, we denote by A star, depending on these distinct scalars, and of course on the vertex X that we fix. And what we have then, so it's a diagonal matrix, and on the diagonal entry, YY entry, we put theta I star every time that X and Y are at distance I. So it's like, again, once we fix a vertex, we say always imagine that we have these vertices partitioned in layers. So it's like a one-to-one now correlation corresponding between the vertices at distance I, so the layers, the layer I with this scalar, theta I star. Okay, we have all the ingredients actually to finally define and deal with this definition of generalized polynomial property. So here we need to consider the eigenvalues of A. Let's say that we have d plus 1 of them, and we order them in this way. So theta 0, theta 1 from the greatest to the smallest, and also consider the eigenspace, corresponding eigenspace Vi for the eigenvalue theta I of gamma, of A, sorry. Then we say that gamma is copolynomial with respect to X. If so, there is a matrix of type star as the one that we just introduced in the previous slide, and an ordering of the eigenspaces of A such that this thing here happens. So we denote this, we refer to this like a tridiagonal action shape of the action of A star with respect to the eigenspaces. In fact, you see A star, let's say, the maps Vij in a subspace contained in Vij minus 1 plus Vij plus Vij plus 1. That's why we say tridiagonal. Actually, this is coming from the usual, this kind of tridiagonal notion, from the usual standard definition of copolynomial. I won't recall that one, but just to say that there is, in that case, there is a requirement for the crane parameters, and actually it's like, okay, they need to be organized in a tridiagonal shape matrix. Okay, by the way, in such a case, A star is a so-called dual adjacency matrix of gamma with respect to X and this ordering. Okay, then what's new in this definition? So we need now to point out some differences or similarities with with the usual one, actually with the situation that we would have for a distant regular graph. So a distant regular graph, this is known, which is copolynomial in the standard usual sense, as a dual adjacency matrix for every vertex. Okay, so the new definition then generalized extends to any graph, simple, connected, and directed, so not necessarily distance regular. And more, this is required, the existence of a dual adjacency matrix for a prescribed distinguished vertex X, not for all of them. Okay, so once we have a new definition, we develop theory. This is what Terwilliger did, and of course, purpose, the aim is like, okay, let's provide examples of graph that have this property, this new sense. Okay, so before doing that, I want to give some motivation that are behind the main steps of our project. Some observation that we need to do on the base of what Terwilliger, with the examples that were found out by Terwilliger, as well as what is happening for this regular graph. So this is what you observe. Often, a matrix of type A star is a dual adjacency matrix of gamma with respect to some vertex X, if together with the adjacency matrix A satisfies a so-called tridiagonal relation that has this kind of a shape, where there are some parameters beta, gamma, rho, reals. Okay. So in such a case, so if there is such a matrix, we say that this is actually definition, our definition. We say that A star is a dual adjacency matrix candidate with respect to X. And we will call then these numbers beta gamma with the corresponding associated parameters with the dual adjacency matrix candidate. Okay, so but then what's the key here? I mean, why do we focus our attention on a tridiagonal relation? Why a tridiagonal relation is the key? Okay, so I want to explain you why this can be working. I mean, so how to get from the tridiagonal relation to a copolynomial property. Again, we need to consider the eigenvalues, theta I, theta D of A, and the corresponding, in this case, primitive idempotents that actually are the projectors on the corresponding eigenspaces. And assume that A star is a dual adjacency matrix candidate. So it means that we have this relation here. Okay. So again, we have this idempotence. And then, of course, we can do the following. Multiply this on the left-hand side and right-hand side, respectively, by EI and EJ. And this is what we get, the second equation. So we can factor out this term, and we get actually an expression involving the eigenvalues, as well as beta and gamma rho. And this is what we are using here. So I mentioned that these primitive idempotents are projectors for the eigenspaces. So actually the row space, column space can be interpreted like the eigenspace as well. So eigenvectors. That's why we have EIA equal again, of course, to AEI and then theta IEI. This is what we are using here. That's why we get this expression. Okay. So now we have this, and let's assume that we know what's going on with the eigenvalues. The eigenvalues are known, are given. Actually, we will see in our examples in particular, we need to work a bit to get the eigenvalues when the graph is not known. So let's say that we know what's happening for the first factor. So the question is, we want to study such a question. Which are the IJ that makes this product EIA star EJ 0? When this guy is not 0. So it turns out that for our aim, finding a dual adjacency matrix, and so let's say an ordering, this is the best. That we have this product 0 for all I and j, such that the difference between I and j is not in this set for some a natural, not equal to minus a, 0, or a. So let's see why. Okay. So once we have this, so this property in the if part, then we have what we want, an ordering of the eigenspaces. So here actually it's like we have a natural ordering. This is the most natural ordering is, okay, order the eigenspaces, ordering the eigenvalues from the greatest to the smallest. And so with respect to that, we get this new ordering. So such that a star is a dual adjacency matrix because we just find out our tridiagonal shape of the action of a star. And and now here again, we use properties from the primitive idempotents. So in particular, let me just explain what we are doing. Bj can be written like EJB, and this is what we are doing here. And of course, in front of a star, we always can imagine to have the identity matrix that in this case will be replaced by this sum. And so now you see that this term is this sum where these products are involved. And we know then what to do. These are then the survivors. I'm not saying that these are for sure they're appearing, but we know the 0 ones. Okay. So in this case, again, this will be a dual adjacency matrix and gamma Q-polynomial with respect to x. Okay, so now let's say we are ready to give the main steps, objectives of the project. So first of all, we focus our attention on a graph gamma that is bipartite and uniform. So I promise that in the next few slides you will get the definition and also motivation why we choose then such a graph. But first, what we want to do? Find sufficient conditions on the uniform structure of gamma such that gamma as a dual adjacency matrix candidate with respect to x. So it means that again there is a tridiagonal relation that is satisfied by a matrix of type A star and the adjacency matrix. And then use this, let's say, strategy that we developed in the first point of the list to construct graphs that are Q-polynomial in this new sense introduced by Terwilliger. Okay, I need first to discuss, let's say, this hypothesis, this assumption that we have. So gamma bipartite uniform. I want to show you that here actually we get some simplification, but it can be also interesting from a combinatorial algebraic point of view of the graph. Let's see why. So first of all, if we have a star that is a dual adjacency matrix candidate for gamma with respect to the vertex x, and then beta, gamma, rho are the corresponding parameters. If gamma is bipartite, turns out that small gamma, so one of these parameters, is 0. Okay, so this you see, simplify, let's say, the calculation. In fact, the tridiagonal relation reduced to this one. So what is not appearing is the term multiplied by gamma. And of course, once we multiply, this is then further to get to the Q-polynomial property eventually. So once we multiply by EI and EJ on the left and right hand side of this equation, now we get again say more simplified version of the previous one in terms of the eigenvalues. Okay, so again, for a bipartite graph, actually, for zeta and y in this position, again, let me also, how to say, recall this. once we fix this vertex, we can always imagine to organize, to partition our vertices with respect to the distance with x. And so we have these I subconstituents, these layers. Okay. So for y a distance I from x and z a distance I minus 1 from x, these are all the possible three walks that we have from y to z. The shapes, the shape, of course, the number will be, in this case, A, B, C. Okay, so before proceeding, let me explain why do we use such a letter as square r. What is the meaning? Why this kind of notation? So let's, for example, check together the red type. From y to z, so we have these layers. I mean, if you're building, you need to maybe imagine like a building vertical one with some floors. So to go down towards x, we need here. Actually, we want to achieve z, but we need to lower twice. So we go back to the I minus 1 subconstituent, then I minus 2. That's why we have L squared. And then raise once to get to z. That's why we are. Actually, same explanation we have for the other two guys. Nothing is changing. Just the ordering. And now, actually, that we explain this, makes sense, this definition. I mean, to provide you with this definition, graph gamma bipartite that is uniform with respect to x. So, again, for every I, from 1 to epsilon, for y and z in these positions with respect to x, we say that the graph is uniform with respect to x if there are some parameters, some, we say uniform error coefficient in the real fields, such that we write this, we have these equations. And this is for every layer like linear dependency relations between all the possible three walks in a bipartite graph. Plus, we should have here some technical conditions on EI minus EI plus FI. Of course, we will use this in our proof, we use this in our results, but not worthy to be recalled here. Okay. Let me just spend some word about the history of this property. Actually, this was introduced by Terwilliger originally for uniform poset. But looking at the Hasse diagram of the uniform poset, it can be easily translated, naturally, let's say, translated to the context, the field of bipartite graph. That's why we require bipartite. So again, why do we choose a uniform bipartite graph? So you see, we have some nice combinatorial properties, also simplification from the, let's say, algebraic point of view, but there is more. And this is something that is referred to the so-called Terwilliger algebra that we can associate to such a graph. Again, okay, so this is what we have, the blue things. I won't recall this because maybe I don't have enough time, but we maybe need like to spend hours to talk about the Terwilliger algebra, modules of this algebra and so on. But this is just because I want to make this like useful, interesting to people that are interested in Terwilliger algebra study. So for such a graph, the Terwilliger algebra with respect to the vertex x, let's say t, has some very nice properties. These two, actually. Just to sum up, every reducible T module is thin, and the isomorphism class of such a module only depends on two parameters, endpoint and diameter, we say, of W. But this is just to say, to recap, that all this theory so help us to understand the algebraic structure as well as the combinatorial properties of a graph that is potentially eventually Q-polynomial. So let me clarify this. I said that we will focus our attention on the sufficient conditions on the uniform structure to get Q-polynomial at the end of the story, passing by a tridiagonal relation. But we can also do the reverse. Let's say this will be next step. Find a necessary condition on the tridiagonal relation, assume that there is such a tridiagonal relation, to get a uniform structure for our graph. So then we will get like a correspondence between, in this case, bipartite graph, between uniform polynomial property. And this, like, it's okay, we have a combinatorial interpretation, finally, of Q-polynomial property, let's say. Okay. So let's come back then to our main objective. We want to find sufficient conditions. So this is like the first version of our sufficient condition, our algorithm strategy to find dual adjacency matrix candidates, of course one, let's say. And yes, you see, this is just translated into restrictions on the parameters of the uniform structure, EI plus, EI minus, FI, actually also the guys appearing in A star. So let's see, let's check it together. If gamma is uniform bipartite with respect to a vertex and we pick some distinct scalars, we define A star, if there are some scalars in the real fields, beta, rho, such that these four equations, actually more because we need to consider this I, but fix I. If this formula holds, then we say that A star is a dual adjacency matrix candidate with respect to X with parameters beta and rho. So, okay, to better understand what's going on here, but actually, since I'm like, okay, uniform property can help us to let's say, get our result. To convince you, I want to show you like a bit of the proof, a sketch of the proof, quickly. So we want to show that for these choices, we have a dual adjacency matrix candidate. So we want to prove that there is a tridiagonal relation of this kind. The most rational thing to do is like, okay, let's then compute the ZY entry of both sides and check if they agree. Okay, so these are actually the expression, the ZY entry for the main three terms appearing in this equation. The first two on the left, the other one is on the right. And what we use here, just, I mean, the properties of our matrices. A star is a diagonal matrix, and this, of course, simplify calculation. And then we use matrix multiplication plus the fact that A is a adjacency matrix. So the cube in the ZY entry will represent the number of walks on length 3 from Y to Z. So in general, actually, the I power way is the number of walk of length I from Y to Z. So this is for I equal 3. Perfect. And this should ring actually a bell in our mind, in your mind. Okay, we have 3 walks, but if it is uniform, we know something, let's say, something more for 3 walks. Okay. Before this, of course, we need to distinguish several cases that we can have for the distance between these two vertices, Z and Y. Actually, for most of them, the equation is trivially satisfied. Why this? Because the graph is bipartite and because we count 3 walks. So if the distance is 0, 2, so if the two vertices coincide or distance 2, the graph is bipartite, so we will have 0 equals 0. And we are counting walking of length 3, so we cannot, that's why we would have 0 equals 0 for distance between Z and Y greater or equal than 4. Okay. So 2 main significant cases are left, actually, distance 3 and 1. But actually, this is what we do. We separately study this special case of distance 3 for Z distance I minus 2 from X and Y distance I plus 1 from X. Okay, I won't mention anything about this, but just that here we use actually the expression that we have for beta plus 1 to get to what we want, this one. Okay, fine. So let's say that we prove this and this is equal 0. But this is the most interesting one from the point of view of the application of this uniform equation. So this is the case in which we have Z at distance I minus 1 from X and Y at distance I from X. And here the uniform equation will play some role, a crucial role, we say. Okay. Okay, yes, because we know that when the graph is bipartite, uniform, these choices of Y and Z, we have these equations. Okay, the uniform equation. But then in this special case, we can like more explicitly, let's say, express these 3 terms appearing in tridiagonal relation. So you see now, this is the number of all possible 3 walks from Y to Z, but we know that in this specific case, these are the 3 walks. So A plus B plus C. And here again, we sum on 3 walks, and so we have just these 3 terms, A, B, and C. Here we are just writing explicitly the value of the distances. So for example, here we have A multiplied by this guy because B is a distance I minus 1 from X, W is a distance I minus 2 from X. The same works for the other guys. So combining all these things together now, plus, let me just recall what we have here. plus these conditions, because now we are imposing this restriction condition on ei minus ei plus fi, we get also in this special case, using the uniform equation, passing through that, 0 equals 0. Okay. As I mentioned at the beginning, I mean, not the beginning, but some time ago, this is the first version of sufficient condition, but we did something better. We developed like an algorithm. So, and I would like to show you, considering, to say, getting some equivalence conditions to the four formulas that I showed before. So now I want to give you the main steps, actually the steps of our algorithms to find a dual adjacency matrix candidate with respect to X for gamma. So the first thing to check is this. Again, we have a graph with a uniform structure, so we will have some uniform parameters. So if this is constant, let's say this turns out that for every I from 1 to epsilon plus 1, this ratio is constant. Then we will denote this guy by beta plus 1. For beta, real, and here you see something more than something that was written before. So it must be different from -2, -1. These are again something that is imposed, like given by the uniform structure. Once we have such a thing, then we can pick some arbitrary scalars, theta 0 star, theta 1 star, this thing, and force theta I plus 1 star to be equal to this, because this is coming from the previous conditions. For fi, that is a function again defined on the uniform structure. Okay. Check then that these scalars, because it's not obvious, that these scalars are pairwise distinct. Check that the function fi appearing in the formula for theta star actually verify such a recurrence formula. And finally, check that these scalars from the uniform structures again positive. If it is so, then we can set rho equal to this guy. Okay, so again, if all these 5 checks are positive, A star is a dual adjacency matrix candidate with respect to X with corresponding parameters beta and rho. Okay. Now we have everything to proceed with the second part of my talk. So the applications, the examples. So examples of graph that work well with this algorithm. So now I will show you 2 graphs that actually have a dual adjacency matrix candidate, and convince you also that this is actually dual adjacency matrix for both of them, and then we will get an ordering, and then that this graph, both cases, is Q-polynomial. But first we need a definition, a new definition. This is actually coming from a previous project paper of ours, and it was about the uniform structure for non-bipartite graph that no, this is a regular graph, yes, with the classical parameter. But by the way, so consider G non-bipartite, fix vertex X, and then define this graph, GF. Well, the set of vertices is the same as before, so as for G, but the set of edges, RF, is obtained from R, removing from this set of edges all the edges that have extremos at the same distance from X. Again, once we fix X, we can always imagine to have this partition of the set of vertices. So we have always these layers. So it's like, okay, in each of these layers, we are deleting the edges. So now maybe you see better that by construction GF is still connected. Now it's bipartite graph. And we call this guy full bipartite graph of G with respect to X. Okay, so again, in this paper that I mentioned before, we have introduced this full bipartite graph. We had some classification results. Among those, the following, the one that is written here, that is the one that we are interested in here for this talk. If G is either Hamming or dual polar graph, then GF is uniform with respect to X. Okay, so now we have a graph GF that is uniform. Okay, observe also that by definition, this guy won't be this irregular. It's not regular, because we remove edges with respect to a fixed vertex. Okay, so we change the valency. So what we have now, okay, let's say a candidate maybe for our algorithm. We have a graph that is bipartite and uniform with respect to x in these two cases. And actually, this is the case. They will be Q-polynomial, passing by the existence of a dual adjacency matrix candidate. Okay, so let's first focus on the Hamming graph example. Consider the full bipartite graph of the Hamming graph, HDN, angle different 2. And so we know that is uniform, and we computed the coefficient. Okay, so I'm not recalling now the definition of Hamming graph, but maybe just the parameters. So D is the diameter, and N, yeah, okay, so the vertices of the Hamming graph, of an Hamming graph, are like n tuples from an alphabet, let's say x. When n is equal to, we get the cube, we get a bipartite graph. That's why we are requiring n different from 2, otherwise we will get, our removal of edges, flat edges, won't produce anything new. Bipartite is bipartite. Okay, so these are now the coefficients, by the way, and they are constant, okay? And then this already like suggests that there is a parameter beta and a parameter rho because they are constant. But okay, so let me like explain what I'm talking about. So then this is the theorem where we apply our algorithm. If gamma is the full bipartite graph of HDN, so of this mean graph, and we pick two distinct scalars, theta 0 star, theta 1 star, and then we consider this formula for theta plus 1 star. So if you remember here in the previous slides for the algorithm was appearing something depending on fi, and this is what we get in that case. So then A star for these choices is a dual adjacency matrix candidate with beta equal 2 and rho equal 4 times n minus 1. Okay, so let's keep it like, let's put it aside. Now let's see what's happening for the dual polar graph. Also here we computed the uniform coefficient. Here, let me just explain like the parameters. So these graphs are defined, such a graph is defined, okay, first we need to consider projective space over finite field, scalar field FB, so B is like prime power. And then D will be the diameter. Then okay, after this we need, the vertices are, we have a, oh no, okay. So on this projective space we have a polar form, we have different polar form, non-degenerate one, and E will be the type of the polar form. And the vertices are the maximal subspaces with respect to this form. And let's say that D is the diameter, but it's coming from the, oh sorry, the dimension of this. So by the way, in this case, we have then this a theorem. Okay, again here applying our algorithm for this choice of theta star, we have that A star is a dual adjacency matrix candidate with these two parameters, beta and rho. Okay, and now this is the first, the last step. How do we get from tridiagonal relation to a Q-polynomial property? So with these two theorems say that gamma in both cases, so for Hamming and dual polar graph, admits some parameters, beta and rho, such as there is a tridiagonal relation of this shape, because remember the graph is bipartite, where A star is a dual adjacency matrix candidate, A is the adjacency matrix. For the things that I explained at the beginning, actually, let's say that knowing the eigenvalues, and here, because of course for these new graphs, the eigenvalues are not known, but we were able to compute this using the uniform property, but from the algebraic point of view. We use exactly what I said for the Terwilliger algebra. So knowing the action of the adjacency matrix on irreducible T-module 13, we were able then to find out the eigenvalues, and there are in both cases 2D plus 1 of them. So here we have that these products are 0 for I minus j, different from 0 to minus 2. So this is this parameter A in this case. And then using the properties of the idempotence, we get this ordering. So it's like with respect to the original one, the natural one, from the greatest to the smallest eigenvalues. Now we are like two consecutive eigenspace in this ordering. The indices actually have difference 2 if they are not the same. So we will have like even, odd, odd, even. So to recap, this is our mean result. If gamma is either the full bipartite graph of a Hamming graph or the full bipartite graph of a dual polar graph with respect to x, then there is a dual adjacency matrix of gamma with respect to x, and this orderings. Okay, and then this means that by definition, that these two graphs are Q-polynomial with respect to a fixed vertex in each case. Okay, let's see that I'm almost done with my talk. Actually, I'm done with my talk, but before concluding, I would like to make a small short announcement. So maybe most of you already know, but it's better like to point out this. Next summer in Slovenia, Kranjska Gora, we will have this very nice event in June from 23-28. And this is the so-called Combinatorics around the Q-on-Sager algebra. So conference to celebrate you know that I mentioned several times Terwilliger, and there is a reason actually. So this to celebrate again the work of Terwilliger 2 years, and these are the main guest stars. So this irregular graph, lemma pairs, again Q-on-Sager algebra, Askew-Wilson algebras, and similar. So I'm just inviting you to join us to something that maybe I won't say this, but by the way, something that we call it among us Terwilliger Fest. So I'm just inviting you to join us there and celebrate together. Okay, I'm done. Thank you very much for your attention.
Thank you very much, Giusy. Any questions, Giusy?
First of all, thank you for that plug for the conference. So about your talk, if you start with these parameters, EI plus, EI minus, and then we consider what are the conditions that lead to the tridiagonal relations, and then eventually the Q-polynomial property. Now you had this algorithm. The success of the algorithm, there must be some conditions on the EI plus, EI minus that make the algorithm work out. Can you say what those are in closed form somehow?
Okay, so these conditions actually are the following: that all the I minus 1 or all the EI minus or EI plus are different from 0, and then we need to check that some matrix, we say parameter matrix, is not singular for every let's say diagonal restricted matrices. So in this algorithm, right now I don't remember if actually they are there. Yeah. Okay, so in this algorithm we use this fact. We say we have these restrictions, so we use this restriction that I just mentioned. Not completely actually, but in some cases we use the fact that it must be not 0, or that we have that this determinant are not these, let's say, submatrices are not singular. So yeah, let's say, but we don't have an equivalent for this condition in the algorithm. We use this in the algorithm. Not completely, just some of them. A few of these matrices for the algorithm must be not singular.
Okay, right. Now you had some slides that had some equations of the nature of so it's going to work out if there exists some mutually distinct theta I stars that satisfy some equations involving the EI plus minus.
You mean this expression for theta star?
Let's see, I think it was a little earlier. So there were, I think there were 3. Right there. Yeah, right there. So the existence of the theta I stars that satisfy these equations must imply some conditions on the original EI plus minus. And can you write those down in closed form?
You mean for theta star?
Right. If you start with your EI plus minus parameters, and and then you want to find the mutually distinct theta I stars that satisfy these equations right here.
Ah, okay. So yeah, so this is actually what we found out. You see, starting from the uniform, from the parameters, this is the
Yeah.
formula, let's say, that we get for theta I star.
So
Because
will
this
that,
Fi is
okay. So are you saying that these equations here work for every choice of the EI plus minus? There's no extra condition on the EI plus minus that is required in order to get this formula?
no, exactly. No, in fact, that's why we cannot say that are immediately distinct pairwise, because let's say potentially we can put everything there right now.
Okay.
Maybe it can be improved using these additional properties, these technical conditions, maybe, yeah. And this maybe can like force to have distinct. But if you just give like this, we cannot say that are distinct, yeah.
Oh, okay, I see. But that's the only I mean, once they're distinct, then it's going to work. So the distinctness is the only issue that needs to be checked separately.
Yeah, because we want that actually start generate the algebra generated by the dual idempotents.
Right. Yeah, that's right. Yeah. Okay. Good. Very nice.